Let me introduce Peter Müller. So this is the last talk for today. Peter is a full professor here at ETH. He's well known for his contributions to program verification, both theory and practice of program verification, object-oriented verification, recently static analysis. He's done a lot of interesting work. So today he'll tell us about this interesting project he's been doing on Viper, the new infrastructure for verification. Right.
Thank you. So given that I'm the 8th talk today, I thought I'd take it a bit easy, and so I'm not going to give you a very technical talk, and instead more a tutorial-style presentation of the Viper project, which we do in my group. So it has contributions from various people, current team members and former team members. So basically, Viper is based on two observations. One is that in the last, say, roughly 10 years, we have seen tremendous progress in deductive program verification. And much of that progress is caused by stronger and stronger SMT solvers. So what many deductive verifiers do is they take a program and a specification and ultimately reduce it to queries in an SMT solver. So they come up with verification conditions in first-order logic and pass them to the theorem prover. And there are many, many instances of such tools, and many of them follow kind of a standard architecture. And that architecture is using an intermediate verification language. So Boogie, for instance, or Y are two of the widely used languages. So the verifier basically consists of a front end that maps the program and the specification into such an intermediate verification language, and then the language comes with a verification condition generator that generates the proof obligations for the SMT solver. And as I said, there are numerous examples. Some of the more successful ones are, for instance, Corel, which is now part of the static driver verifier at Microsoft, the Daphne, which powers the Ironclad project, for instance, which you might have read about, from the people in Paris, Spec Sharp for C#, VCC for C, and so on. So that was a very positive development. It simplified the development of provers or of verifiers tremendously, and people seem to find that useful. Another major advancement in program verification that happened roughly during the last 10 years is that people have discovered and explored separation logic and similar permission logics, which have nice answers to the question, how should we deal with heap data structures, but also how should we deal with concurrency. So in principle, these verifiers also take a program and a specification, the specification written in such a permission logic, such a separation logic, and ultimately also use SMT solvers, for instance, to handle arithmetic. But in between, they typically do not just translate the entire verification condition to SMT, which is possible. In Shellis, for instance, we have done that, but most people seem to prefer to write verification tools that have a dedicated handling of the separation logic formulas. So separation logic is not just the first-order logic, so you cannot directly map it to SMT, and so you do something else instead. And many tools, like for instance JSTAR, Smallfoot, Verifast, instead use some symbolic execution engine where they handle the heap reasoning or the permission reasoning internally and only use the SMT solver as a backend for, as I said, for instance, arithmetic. And now the disadvantage of that approach is that if you want to go ahead and build more verifiers for more different languages, you will have to write new such verification engines. So the only part that you really reuse is the prover, but everything else is developed more or less from scratch for every new tool. So this is much harder to experiment with, to prototype, or just to build such tools. So in Viper, we try to combine these two major trends. We try to make available a verification infrastructure that makes it easy to build new verifiers and it makes it easy to reuse large chunks of the work. But we also would like to support permission logics such as separation logic. So here's an overview of what Viper looks like. So on top, we also have a front end that encodes some source language and specification into our intermediate language. And now for this intermediate language, we have two verification backends. One is an encoding into Boogie, so a verification condition generation that ultimately sits on top of an SMT solver. And we also have a symbolic execution engine, just like Smallfoot and Verifast, for instance, which ultimately sits on top of the same SMT solver. So we have two verification backends, and you are free to use either of them or both of them to verify your programs. In addition to that, we have an inference engine based on abstract interpretation, whose job it is to infer auxiliary specifications, such as loop invariants, for instance, and reduce the annotation overhead for the programmer. And the goal is, by making all of this infrastructure based on an intermediate language, this entire infrastructure can be reused when people want to support new programming languages and new specification languages. So you just, like in the Boogie setting, you build new front ends on top, and the rest is supposed to stay more or less the same. So why is this interesting as a research project? Well, the scientific challenge there is to come up with an intermediate language that is so expressive that it allows you to encode many different verification approaches on top. Different logics, different verification techniques, different source programming languages. So you would really like to make this language as expressive as possible, but at the same time you would like to retain a high degree of automation in the verification backends, and you would like to retain the possibility to run abstract interpretation as an inference. So to resolve this tension, that's basically what we are struggling with every day in our research. And what I would like to do in this talk for the rest of the time, I will just give you a demo of how Viper works, how programs in this intermediate language look like, and I will try to show you some of the features that we found particularly useful as features of an intermediate language to encode all kinds of things on top. So let me start by showing you a little bit of the assertion language. So as I said, we support permission logics. More specifically, we use implicit dynamic frames, which are in flavor very similar to separation logic and have also been formally connected to separation logic, so it doesn't really matter which one we use. So in our assertions, we have access predicate of this form, which basically says in the current state, we do have the right to read and write the location e.f. We can combine that with information about the value in the location, so we can say we have the permission to access x.f, and by the way, x.f is positive. We support fractional permissions, so we can divide a permission up into smaller chunks, like for instance here we have half a permission to x.f, and that's very useful if you want to support concurrent reading while still having exclusive writes. So what basically that means is whenever you have a non-zero fraction, any positive value you can read, but only if you have the full fraction, then you can write, okay? And this is what you can, how you can support that. And our conjunction, even though we write it like a Java conjunction, really behaves like a separating conjunction in separation logic. So this is a multiplicative conjunction here. So taking half a permission to x.f and another half permission gives you the full permission. So this is not equivalent to just half a permission. This expression together gives you a full permission. And now the two key operations that we use in our verification engine are called inhale and exhale, and they operate on assertions. So inhaling an assertion A means look at all the permissions that are mentioned in this assertion based on the assertions that I showed you on the previous slide and add them to the current state. So you obtain additional permissions. Moreover, take all the pure logical bits like x.f greater 0 from the assertion and assume that they hold. Right? So you can think of this as a permission-aware form of assuming a property. And exhale is correspondingly the permission-aware assert operation. So what exhaling an assertion means, look at all the permissions that the assertion mentions. First, check that you actually have them in the current state, and if so, remove them. Moreover, take all the logical bits of the assertion and prove that they actually hold. So it's really like an assert. And then there's one extra twist which makes things a bit more interesting. Once you have given up an assertion that you previously had, you should not remember anything about the value of that memory location, because giving up an assertion could, for instance, encode that you give the permission, giving up a permission could, for instance, mean that you now give the access permission to another thread, and now this other thread could now go ahead and modify the location, so whatever you knew about that location might no longer be valid, okay? So exhaling a permission implicitly contains something like a havoc of the memory location, so you forget everything that you used to know. So let me show you in a small demo how one works with these primitives. So let's imagine we have a class C, which has a field data of type integer array. And now I have a foo method that acquires the lock, then iterates over this array in a not very interesting fashion here, and then at the end, we release the lock again. So let me switch into an editor in which Silver runs. Is the font large enough for people in the back? Yes? Okay, thank you. So let me show you how we encode that. So just like Boogie, for instance, our intermediate language is a simple procedural language, not object-oriented. So I don't have classes, but I have fields. And the idea is that if basically every object, every reference has every field. So our intermediate language does not have to be executable in an efficient way. It just needs to reflect the semantics of the program that we need for verification. So I don't need to be careful about how many fields an object has. And then I have methods, which are really procedures, really. So it takes this object of type reference. It has a precondition that this is not the null value. And then we will acquire the lock, and I will show you how to encode that. We read the length of the array, which I encoded as a sequence up there, just as a mathematical sequence. We iterate over it, and at the end, we want to release the lock. So one thing that we might want to do is we might want to encode that at some point we get the lock, and at another point we release the lock. And we could do that by regarding a lock just as a resource, like in separation logic, and we could use permissions in order to encode whether we have a lock or not. So for instance, what I could do is I could introduce a field holds of some type. I will never use its value, so the type doesn't really matter. And I could say, okay, acquiring a lock means that I get the permission to this holds field. Doing here, thanks. And releasing it means that I give it up again. So remember, exhaling a permission means first checking that we have it. So you could not release it without acquiring it first and then giving it away. Okay, now we can verify this. And this leads to a verification error. And the verification error says that I do not have the access permission that I need to access this .data. Why is that? Well, on my slide here, I use this Java-style annotation to say this .data is guarded by the lock this. So that's basically like a monitor invariant, like a lock invariant that says the lock contains the access permission to this field. So every time you acquire the lock, you get it. Every time you release the lock, you have to give it up. So we can easily encode that. I can just say, okay, whenever I acquire it, I also inhale the access permission to this .data. And when I release it, I do the opposite. Right? And now with this encoding, I can verify that. So here we are. I might also want to verify, for instance, that locks are never leaked. So when I acquire a lock, that I leak it eventually. So I can do that by just putting another proof obligation at the end. So what we can do is we can iterate or quantify over all the, we say heap chunks, over all the resources that we have in our symbolic heap. And for performance reasons, we say which fields we are interested in. So that's why I put holes into parentheses. So what I say here is, look at the current symbolic heap, look at all the parts of the heap that talk about the holes field, and look at the receiver and call this receiver X. Thanks. I hope the tool would have told me very soon. Or the syntax highlighting, thank you. So if I want to say that I have no such resources because I have released all the locks that I ever held, I can just put the false there saying that this quantifier ranges over the empty set. And now if I verify this, this should succeed. And now, for instance, if I forget to do the release, like this, let's say, and I try to verify this again, then I will find out that this leak check fails. Okay, so that's this basic idea of being able to reason about permissions directly on that level. As you saw in my example here, I took a shortcut. I used a Java array and then encoded it as a mathematical sequence, which is of course not the same. But of course we could also encode something like arrays, which introduces another feature that we make use of a lot. So in our intermediate language, we can define mathematical domains. So here I have a domain that I call arrays. And that allows us to introduce like more vocabulary. And in particular, we can even define features such as arrays as just another mathematical domain without having native support for arrays in the language. So the way I do this is I say I introduce two functions, one for locations and one for length. So if I take an array and an index I, then lock gives me some reference. Basically, I represent every slot, every element of the array as a reference, and then use some predefined field name to actually get to the value. And then length gives me the length of each array, and now I give some axioms about these uninterpreted functions that tell me how they behave. So for instance, I can say that two locations are the same only if the arrays are the same and the index is the same, or I can say that length is always greater or equal to 0. And by defining such theories, such domains, we can, as I said, extend the vocabulary, but we also have the possibility, instead of just an unstructured way of introducing function symbols, that we can special case such domains in the abstract interpretation and, for instance, recognize that we have such an array domain and later interpret it using, for instance, an array abstract domain. Another feature that we use a lot is a fairly expressive permission system. So far I mentioned access permissions, I mentioned fractional permissions, but we can actually do many more advanced things, and this example shows one of them. So imagine that we have an eval method in, say, a Java-like program that sits inside an abstract syntax tree. So it evaluates an expression in a given state. And let's assume the state S has a field map, which maps variables to values. Okay? Then what we would like to say is that we need access to this field s.map to look up values with some permission pi. And then this map should be non-null. And when we terminate, we give back this permission such that eventually the caller can assemble all the fractions and modify the state again. Okay? Now the problem is in classical fractional permissions how you pick the pi. First of all, any concrete value that you put here, like a half, a third, a 1/8, whatever, seems completely arbitrary. So you put too much information into your specification because all you really want to say is, I want to be able to read this map. Moreover, typically when you have such fractions, you would like to be able to divide them further. So for instance, you might have an implementation of eval here of a binary expressions that evaluates the left and right sub-expression concurrently, right? So that means you need to fork off two threads, and now each of them needs permission to the state. So now if you put some constant here for pi, you won't have enough to give both of them what they need. So you need to somehow split the pi further, and you need to be able to somehow parameterize what kind of permission you need here. So what you really want is a much more abstract way of specifying that, something like, all I want to make sure is I can read this map. Okay, and what that's supposed to mean is, give me some non-zero values that I can read, and I promise whatever you give me, I'll give back. And so this is something that we support in our intermediate language very easily. So we have a type perm, which stands for permission amounts. So I can write the eval method by giving it an extra parameter perm, which stands for the pi. How much permission do I want to give into it? So I take p and I return p. Okay? And the nice feature is that our verifier allows you to leave this p unspecified and to just constrain it in a suitable way. So when we look at the fork statement, so these two exhales encode the two fork operations, what I can do is the following. I can say, give me some fresh permission amount RD, and now this constraining operation says, constrain RD such that all of the exhales in this block succeed, and moreover, there's still something left for the caller. Okay? And now the verifier ensures that there is such a value. So if you try, if this constraining block contained exhale operations such that you cannot satisfy the constraints, so for instance, you exhale RD and 1 minus RD, then you cannot satisfy the constraint that something will be left over. So we verify that this is the case, and we pick the RD automatically, or in fact, we never pick it, but conceptually you can think of the theorem prover picking a value, but all we need to do is we just need to suitably constrain it. So when I verify this, this will succeed. And to show you that we actually know for sure that we don't give away everything that we have, so that RD plus RD cannot add up to P, I could, for instance, add another proof obligation that says state.map in this state is the same as old of state.map. So this we only know if we have some permission left, because if we had given all the permission away, remember, then exhale would make us forget everything we knew about the location. So if this verifies this is a an argument that shows that we still have some permission. So that's very convenient because typically we never have to work with concrete fractions anymore in the program, and we can have a much more abstract specification. Another feature that we use a lot is that we support, in contrast to most separation logics, heap-dependent functions. So typically when you look at code like Java programs, they contain many side effect-free methods that really behave like functions. And it's often very convenient to use these methods in specifications. So for instance, when you want to specify what a collection in Java does, you will have to use the equals method for that, because membership in a collection is defined relatively to what equals does. Okay, so being able to use equals in a specification is very useful. So what we would like to do is we would like to encode such side effect-free operations like the length of a list or the item add operation of a list as a mathematical function rather than a procedure, and use it inside specifications. And the challenge there for building the verifier is if these functions are recursive, like in these cases here, you have to make sure that your SMT solver does not just wander off and unroll these function definitions indefinitely. You need to have smart ways of controlling how this recursion is handled inside the prover. So let me show you that very quickly. So we have in our language not just methods, but also functions, and these are really mathematical functions, so no side effects, deterministic results, must terminate, and so on. And they can be recursive, as you can see here, for instance. And we can use these functions in method specification. So here, for instance, I have a set operation that uses len to restrict the index I, or that uses item add to describe what the operation does. Okay, and now I can also verify that. That comes back relatively soon, and basically here you can see that we have the recursion under control. The prover does not just instantiate the definition indefinitely. And then I would like to show you one last feature of Silver that we use very, very often, and that's a feature that allows you to make the properties that you check at some point in your program and that you assume at another point not symmetric. So when you encode program semantics, often you want to check things that are slightly different from what you assume in another place. Like in theory, this is the same. You check the precondition before the call, you assume it inside the method. You check the post condition before you return, but you assume it at the call side. But often you have situations where you want these two properties to be different. So one example, for instance, is if you want to encode certain proof principles. So if maybe I want to, whenever I assume a property, I would just like to assume that for all n, P of n holds. But when I prove it, I want to prove it by induction. So I want to prove P of 0, and for all n, if P of n minus 1 holds, then P of n holds. So that's one example where you want to be asymmetric. Another example is when you have properties that are justified elsewhere. Maybe in a soundness proof, maybe by your type system, maybe by another static analysis that you ran before you did the encoding into our intermediate language. So for instance, assuming at the beginning of a method that the type of the receiver is a subtype of the enclosing class T is something that is justified by the type system. You don't need to prove anything to do that inside your verification tool. And you also have the dual of that. Sometimes you just want to prove properties but not assume them on the other side. For instance, if the proof obligations are somehow context dependent. So earlier we saw this leak check, and this leak check is something that might be true inside a method, but it's not necessarily true in the caller because we do modular verification, so the caller might hold different resources than the callee. So it would be unsound to check this here and also assume it on the other side. It might not be true on the other side. So you can also include a check without an assumption. So most verifiers support some such aspects. So for instance, in Boogie, let's say you have things like free post conditions and free preconditions, which allow you to do things like that, assuming properties without checking them. But we have a much more flexible mechanism by just having so-called inhale-exhale pairs. So it's a pair of assertions where we use the first component of the pair when we inhale the assertion and the second one when we exhale it. So let me show you that feature also in a demo. So here I introduce a domain which has a function sum, and sum is supposed to return the sum of the first n integers. And I define it to say if n is less or equals 0, sum is just 0. And otherwise, sum of n is n plus sum of n minus 1, right? So now I can think of a method induction which has as a precondition that the sum of the first n numbers is n plus 1 times n over 2. Okay, so that's a well-known thing, right? And then I use this precondition to prove that the sum of 10 is 55. However, I also have a caller down there, and that caller will not be able to establish that precondition because that precondition requires induction, and our tool does not do induction automatically. So when I try to verify this, it will fail. Okay? So what we can do is we can take this out and instead use a paired assertion. So when we inhale it, that's the first line here, we take the same precondition as before. But when we exhale it, then we do it by induction. Okay, so we prove that sum of 0 is 0, and then we do the same thing to go from n minus 1 to n. Right? And now when I verify this, then I can prove it very easily because now it's, of course, an almost trivial proof and the induction has been taken away. So what that means is if your front end has a way of figuring out when to do induction or on what to induct, maybe from user input, maybe from some heuristics, maybe from other sources, then you can encode that very easily into our intermediate language, and we can make use of that during the verification. So I mentioned several times that the main goal is to make it easier to write front ends that sit on top of our infrastructure and to make their lives easier. So far we have 4 front ends. The first one is Chalice. Chalice is a tool that Rooston Leno and I developed a couple of years ago and which initially sat directly on top of Boogie, but it's using permissions, and so we thought it would be interesting to re-implement the same language on top of the Viper infrastructure. And it turns out this new encoding is much, much simpler. In fact, if you compare the size of the Boogie program that the old Chalice creates and the size of our program that we create, these are really orders of magnitude between them, and not binary. I mean, real orders of magnitude. We also have, which shows that the higher abstraction level that we have compared to Boogie makes writing such front ends easier. We have a front end for a very small subset of Scala, just to explore how we would translate certain language features. We are interested in growing that, but so far it would be a wrong claim to say we have a verifier for Scala. It's really a tiny front end so far. And other people have used our infrastructure as well. So for instance, at the University of Twente, they have written a verifier for Java on top of Viper, and they have written a front end for OpenCL because they're interested in GPU programming, which leads to very, very different proof obligations because this is very array intensive. So you need like you write different kinds of programs, different kinds of specifications. So it was interesting to see to what extent we can support that as well. And we are currently working on or discussing 4 additional front ends within ETH, other groups at ETH, and at other universities. So we might very soon be able to show another few front ends here, including front ends for dynamic languages such as Python and JavaScript, or front ends for languages that support fine-grained concurrency, things like log-free data structures. So let me summarize. So I claim that Viper is useful for 3 main purposes. The first one is to actually build verifiers that use permission logic. So to build, for instance, separation logic verifiers, we give you an infrastructure that gives you many reusable bits, and you can put a front end on top of that. I personally also find it very useful to prototype new verification techniques. So typically when I come up with a new verification technique, before I implement a full-blown tool, I just encode examples manually. Before I started working on permissions, I typically did that in Boogie. Now I typically do it in Viper, and I encode examples manually and see to what extent my technique actually works. And if those experiments go well, then maybe I implement a real tool for some proper experimentation. And finally, we found it very useful to experiment with having different backends. I believe we are the only tool that has both a verification condition generator and a symbolic execution engine as backends. So it's often very interesting to compare these two. And it turns out some things are much easier to implement in one or to support in one technique than in the other. Sometimes we get different performance behavior. Sometimes we get different outcomes, which often points us to bugs in the code. So having this kind of flexibility is nice, and of course in the long run it would be very interesting to let these three tools, the abstract interpretation and the two backends, not just work side by side, but to actually integrate them much more closely. The current work basically focuses on three major directions. One is to increase the expressiveness of the intermediate language, to be able to encode more and more source languages. To encode more languages and logic, so that means to build more front ends, but not just different variations of what we already have, but really things that have a very different nature. And in particular also to improve the inference, which is currently very basic, but I think it's really important to reduce the annotation overhead by having a strong abstract interpretation component there. If that feels like something that might be worth spending some time with, if you want to try it out, there is a web version which is not super fast, but you can still use it at least. And we are working on making it perform better. So that's viper.ethz.ch. So you get a website like you might also know from Rise for Fun, for instance, where we host our tool, and there are lots of examples, and you can work with the different backends and just try out examples and see how the tool behaves. And with that, I conclude. Thank you.
I was surprised in your picture that the arrows only go down, and you don't have an arrows going up. Because when something goes wrong, the proof, it will come from Z3 that cannot make it. Then you go to Boogie, which is something no one understands in Scala.
Yeah.
And you see, the problem is how do you report the problem that you have inside the system to the original user?
Yeah, so all the errors, in fact, go in both directions. So you can basically do two things. Either on the way down, you preserve enough information to be able to map error messages back. So that's mostly information about program locations and about variable names. Or what we also sometimes do, which is, for instance, something also that Boogie clients do, is we pass the error messages down along with the code. So the encoding can already say, well, prove this property or else display this message. So you formulate the error message up here, and you just pass it down to the tool chain, and you emit it at the bottom. But I mean, I absolutely agree. This is a crucial point.
So you mentioned very fast in the beginning. So apart from the generality, it looks like this design has a lot that is similar to that, but also different. Can you comment on what's different and what are the advantages and disadvantages of how the tool is set up?
Yeah, so, so there are different answers depending on what aspect of the design you look at. So if you just look at the tool architecture, Verifast doesn't have a verification condition generation, doesn't have an abstract interpretation, but the symbolic execution is very similar. So the way we started out is we first learned what Smallfoot and Verifast do, and we imitated much of that, but we have also extended much of that since, for instance, to support magic wands and iterated conjunction and other features. So that's on the technical level. On the philosophical level, I think the difference is that, that Verifast aims to be a proof checker, right? So it is willing to live with a very large overhead. A factor of 10 is not unusual in terms of like the annotation to code ratio, and is, of course, then very, very expressive, right? There's hardly anything that you cannot do with Verifast. We try to build a tool that has a much higher degree of automation and therefore might sacrifice expressiveness in various places. So I believe that we inhabit different points in the design space, but in nature, our tools are certainly similar, very similar.
Is it easy for your end users to understand fractional permission and so on? Do you have some experience on the easiness of using this concept, which is a bit abstract, in fact?
I don't have any data. So I used to work with people from industry, for instance, on the SpecSharp project, and I was often shocked by how little one can expect from developers. So my experience with SpecSharp was everything worked surprisingly well as long as verification succeeded. So they were willing to write specifications, and when they got a nice result, everything worked well. As soon as they ran into verification problems, they were completely lost. Kind of debugging a verification issue was beyond their capabilities. I assume that these problems are more severe here because the annotation language is much more complex than SpecSharp's. I mean, SpecSharp is a designed by contract language, right? So it's just Boolean expressions of the programming language. This will be harder here, but I cannot give you actual evidence because I don't have end users yet.
Yeah, I was just wondering whether this problem is actually not pushed to the developers of the front ends. I mean, if I'm as a developer who writes my Java programs or whatever, then I should probably concentrate on the Java specifications and whatever is passed in the translation to the intermediate language.
That's a very good question. Yeah. So in principle, yes, but you could also imagine other models. So for instance, one of the ideas that we were playing around with is whether we should build a front end for Rust. So Rust is a very strong type system, and it seems like the type system gives some guarantees about ownership that we could use to generate permission specifications from that. And then the programmer would ideally never ever see the permissions. But whether or not this is actually possible, I could just make a claim now. I believe there's a good chance, but we haven't done the work yet. So ask again next year.
I see in the OpenCL one, does it use, can it reason about floating point values?
No. No, we don't do any floating point values. Thank you.